To understand this, we first have to talk about light. So we're going to make this little detour through physics. Light and how it interacts with atoms helped scientists to understand what the atom was. Light is a form of electromagnetic radiation. We pretty much just take light for granted, don't we? We don't really think about it, and yet we all have a lot of experience with light. The sun shines and it becomes light outside. At night, if it's dark, you turn on the light, you know, a lamp or something, and then you can see. But what really is light? It's electromagnetic radiation. This term radiation sounds scary to a lot of people because you think of radioactive stuff and things that are bad for you. But radiation is just a form of energy. And it depends on how much energy the radiation has, whether it is dangerous or not. Light is just a type of energy that travels through space at a constant speed, 3.0 times 10 to the 8th meters per second. That meters per second probably doesn't mean much to you. That is 186,000 miles per second. Light can go 186,000 miles in a second. That is fast, right? You know what we call this number? 3 times 10 to the 8th? The speed of light. Yeah, seriously, it's called the speed of light. It's light speed. And all light travels at the same speed. And then when you get into rocket science and traveling in space, there's enormous distances. And you've probably heard of the term light year. A light year is the distance that light could travel in a year. If it can go 186,000 miles in a second, it can really go a long way in a year, can't it? So it's energy. Light has properties of waves and of particles. We don't usually think of light as being particles. Do you feel like you're being bombarded by particles of light right now? I don't, but we are. Let's look at light behaving as a wave. You've probably seen something like this happen. You've got a still body of water. It could be in your bathtub or your sink or a lake. And if water drops into it, little droplets fall, it causes these ripples, right? And they radiate out in concentric circles, and they just keep going. These are little tiny waves. And that's how the energy from these droplets falling is transmitted. They're transmitted in waves. So the wave carries energy as it moves through the water. And if you've never thought of a wave as energy, have you ever been to the ocean and stood in the surf? And a big wave comes and you don't get out of the way, what happens to you? It flattens you. Is there energy in that wave? Sure there is. There's a lot of energy in a big wave on the ocean. Comes and knocks you over. So these little waves, these don't have a lot of energy, but they carry energy. Characteristics of waves. We talk about the wavelength. It's the length of the wave. So the wave goes up and down and up and down and up and down. And you could think of this level here as being the surface of the water, and there'll be part of the wave that goes above and part that goes below, and it'll travel in one direction. What we call the wavelength is the distance from one peak to the next peak. And some waves have longer lengths than others. And this is given the symbol lambda, which looks like an upside down lowercase y. It's a Greek letter. For visible light, the wavelength of the light determines what color it is. So when we see red or yellow or blue, we're seeing light that has different wavelengths, and our eyes detect that and send messages to our brain that we interpret as color. If we take a light source, such as an incandescent light bulb or the sun, and have it go through a slit and into a prism, we see a rainbow is formed. The prism separates the light according to its wavelength. And the order of the colors is always the same. It's red, orange, yellow, green, blue, indigo, and violet. That's why sometimes when a child draws a rainbow, They draw the rainbow over the little town or something, and you look at it and you're like, there's something wrong with that rainbow. Because small children don't usually realize that the colors of a rainbow are always in the same order. And if you draw them in the wrong order, it doesn't look right. So this is white light. White light contains all the wavelengths of visible light. And when we pass it through a prism, it gets separated into the different colors. A rainbow that you see in the sky is just light from the sun passing through raindrops in the air that are acting as prisms. Sometimes you can see it in your front yard when the sprinklers are running too. If you're at the right angle, you can see rainbows. When we see an object as having color, like this woman's shirt is red, it appears red to us because the white light from the sun is hitting her shirt, and the shirt is absorbing all of the colors except red, and it's reflecting the red light. So all the colors of the light get absorbed by her shirt, the red light gets reflected, and that comes to our eyes and we see it. Something that's black is going to absorb all the wavelengths of light and reflect almost no light. That's why it's really hard to photograph like a black lab dog or any black animal, because they're all dark and they look like a blob when you try to photograph them. If we see something as white, like this whiteboard looks pretty white, that's because it's reflecting all of the light. Okay? And that explains why, like I've got a black sweater on. If I go out in the sun in the middle of August, I'm going to get really warm, right? Because something that's black absorbs more of the light. It absorbs all the different wavelengths. And light has energy, right? If you're out in a white shirt, the white is going to reflect most of that light, and so you're not going to get as hot. That's why white cars and white minivans are real popular around here, because they don't get as hot in the parking lot in the summer as black ones. Black ones get really hot. They look super cool, but man, they're hot inside. Another property of light is its frequency. Frequency. This looks like a V, but it's not a V. It's new. Ooh, that's not a good color. Let's go with white. So this is straight and this is curved. So it looks like a lowercase v, but v is velocity and nu is frequency. Frequency is the number of cycles or crests that pass through a stationary point in 1 second. So if you've got somebody standing, maybe they're standing in a lake. I grew up in Minnesota. We didn't have oceans. They're standing in a lake, and these waves, the wind is blowing and the waves are coming at you. The frequency is if you start counting how many of these crests pass you in 1 second. That's the frequency of the light. And the frequency is going to have units of like cycles per second, which is the same as hertz. You've maybe seen that. Hertz or kilohertz. The wavelength and the frequency are inversely related. Light always travels at the same speed. So this wave of light is always traveling, its velocity is the same. This particular wave that I drew here has a relatively long wavelength. Right? There's the wavelength. Let me draw a different wave. And there's the wavelength for that one. Which one has the shorter wavelength? The yellow one or the white one? The yellow one has the short wavelength. But if this funny-looking person is standing here counting yellow waves and white waves coming through at the same speed, is he going to see more yellow or more white ones? More yellow peaks, right? Because they're closer together. So that's high frequency, small wavelength. Large wavelength, low frequency, inverse relationship. That is light behaving as a wave. But light can also act like a stream of particles. You kind of think of one of those, either a pitching machine or one of those things that'll shoot tennis balls at you. And you've seen in the movies sometimes they go berserk and they're shooting the balls way too fast, right? So that's kind of what I see. It's a beam of particles, a stream of balls being thrown at you. But the particles have a name. They're called photons. Where have you heard the word photon? Pardon me? Biology, really? Where's probably the first place you heard photon? Star Trek, yes. Seriously, it's on Star Trek. Photon torpedoes, right? They're always firing photon torpedoes. Photon torpedoes are light energy being shot out. So that's what a photon is. So it's a particle or a packet, a piece of light. It's kind of hard to think about. Like, you don't say, oh, I'm having cookies. I'd like a piece of milk, please. How do you have a piece of milk, right? It's craziness. How do you have a piece of light? But you can have a piece of light. So the amount of energy, remember light is energy, the amount of energy that's carried in that packet, that photon, depends on the wavelength of the light. If we have a shorter wavelength, we have greater energy. And that's because light waves carry more energy if their crests are closer together. High frequency, short wavelength. So let me draw some ugly waves again. I'll just keep with the same colors. So there's our short wavelength, and here's our long wavelength. Now just looking at those, which one looks more energetic, the white one or the yellow one? The yellow one. I think of somebody jumping up and down fast, right? They are going at the same speed, right? They're going at the same speed. But this one carries more energy because it's going up and down faster. And you think, too, of waves at the ocean. If they're coming quickly at you, is that going to knock you over more than if they just come very slowly? If you get hit by a wave once every 20 minutes, no big deal, right? But if you're getting hit every 30 seconds, there's a difference, right? So the faster the peaks go up and down, the more energy. Is that a new section? Yes, it is.